Hello everyone. So again, welcome back to the latest lecture session. So we have looked at different aspects until now. I think looking at or summarizing what we have been up to, I think we looked at risk assessment in great detail, and then the relevant law and the regulations, and then the aspects related to the TSDF operation and so on, let's say, right? And then we are now going to move on to the next major aspect. And what is that about? That's about the remediation of contaminated groundwater, right? So in this particular set of lectures, I guess we are going to look at how do I remediate a particular contaminated or a site with contaminated groundwater, let's say, right? So there are different options, some of which we are going to look at and such. But before I go further, let's say I'm a layman and I have no clue about how to go about that. And there are obviously different sources of information out there. So how do I choose from one particular method over the other when I'm trying to look at remediation of, or trying to choose which particular way, or how do I go about remediating a particular contaminated site, let's say. How do I do that? I have this particular treatment technology screening matrix developed by the EPA, if I'm not wrong, okay, the US EPA anyway. So this gives you an overview of the different technologies available for different kinds of contaminants, let's say, and in which cases or in which particular aspects does it fare better, in which aspects does it fare poorly, as in does it fare better in its efficiency to treat the particular contaminant of the in the groundwater, let's say, or does it fare better in terms of cost, does it fare better in terms of practicability or feasibility of application, and so on. So let's just try to look at that, or what we have in this treatment technology screening matrix, let's say. So here we have the relative overall cost and performance, operation and maintenance, capital cost, reliability and maintainability, relative cost and timeline, and also obviously development status, as in is it mostly at the research level, or has it been put in practice since quite some time, and so on. Development status, treatment train, and availability, I guess. And then out here we have the different types of compounds. I have the non-halogenated volatile organic compounds, I have the halogenated volatile organic compounds, and so on, right? And fuels, as in hydrocarbons and so on, petrol, diesel and such, inorganic compounds, radionuclides, explosives, and so on, right? So I have different classes of contaminants here, right? Different classes anyway. And out here I have different types of treatment techniques. So here I have in situ biological treatment, in situ physical and chemical treatment, thermal treatment, and so on. So let's say I have a particular case of underground storage tank, let's say, as in our petrol bunks and such. I mean, where do they store the petrol and diesel now? You have these underground storage tanks, lined, let's say, storage tanks, and typically from experience we know that they over time and also due to the poor quality of construction and such, you have leaks developing in these underground storage tanks. At least in Indian context, they are not detected, let's say, and you have considerable pollution of groundwater and soil, let's say. So how do I go about choosing which particular treatment technique would be apt to the particular situation? So here let's say I am concerned with fuels, let's say, okay, and looks like which particular technique is relatively better, let's say, and I guess it does say bioventing, yes, and obviously the relevant costs and such seem to be fine too. I mean, costs and such. To understand that, I guess we need to look at the legend here, right? So we have above average performance, right, average performance, below average, and so on. And again we have the reasons why this particular method is listed as above average, average, or below average. Different aspects being, let's say, for example, in treatment train, is the technology only effective as part of the treatment train or as standalone? For example, does it need to be set up in conjunction with other treatment techniques, or does it work standalone too? So standalone, not complex in terms of number of media treatment technologies, maybe one routine technology in addition, right? Low degree of operation and maintenance, low capital investment, and so on, time required relatively less, and so on. Availability, as in there are quite a few people who can get the job done for you, and the effectiveness has been demonstrated in full or pilot scale. Again, we just try to look at what we need to understand when we have this above average classification, I guess. So let's go back to what we have here, let's say, and for fuels looks like obviously it does a pretty good job, right? And obviously we are going to look at why. I mean, here I am just talking about bioventing or bioremediation, and enhanced bioremediation obviously doesn't or fare as well when compared to bioventing, especially in the context of operation and maintenance, right. Because it's enhanced bioremediation, as in you need to put in or you need to have extraneous inputs from time to time, and obviously relevant monitoring too, and in that context your operation and maintenance costs are going to be higher, and also the capital costs. But with respect to fuels, this particular what do we say summary of all the available literature and knowledge bank out there says that these particular bioremediation in situ biological treatment techniques are pretty good for remediating fuels, right. So again, one particular way to go about choosing or narrowing down the relevant options. So looking at this screening matrix, you can narrow down the relevant remediation technique or screen the different remediation techniques. So once you narrow down your options to 3 or 4, you can then look at them in greater detail with respect to the actual what do we say feasibility at that particular site, as in site conditions vary, right. So obviously you can use this particular matrix to narrow it down to what you are looking at, and then go forth. For example, if I am looking at inorganics, let us say, or heavy metals, let us say, which particular methodology seems to be better here now? So obviously not bioremediation, not enhanced bioremediation, and so on, let us say, and other level of active, I mean I am trying to understand what this particular legend means, I guess, or symbol means. Level of effectiveness highly depend upon specific contaminant, its application or design. So that is what it means when we have this particular symbol for bioremediation for the inorganics or the heavy metals. So which particular methods can I screen out or screen in, let us say, or choose when I am looking at remediation of sites contaminated with heavy metals? Now I am going to look at electrokinetic separation, let us say, and also soil flushing the soil, yes, that is one particular aspect, or solidification stabilization, let us say, right. And in this particular class we are certainly going to discuss this soil flushing and solidification and stabilization, let us say. And what else? Obviously chemical extraction, oxidation or reduction, right, again solidification and stabilization, but this is ex situ, I believe the other one was in situ, right. So in such a manner I can narrow down the relevant what do we say options that I have, and once I narrow down the relevant options, then I can analyze them in greater detail to see if a particular technique is applicable to my particular site or not. So obviously there are different treatment techniques. Let us look at some of them. As we discussed earlier, or briefly looked at them, we have biological treatments and different classifications between in situ and ex situ treatments for both the biological and physical and chemical treatment. For physical and chemical, we have chemical oxidation, electrokinetic separation, fracturing, soil flushing, soil vapor extraction. These are all aspects we are going to discuss in great technical detail now, solidification, stabilization, and so on, right. So we have different such aspects out here, right. Again ex situ physical treatment and so on. So in particular case, let us say you cannot treat it, what can you do? You will try to contain the particular waste, let us say, and again for that particular case they are looking at physical barriers or deep well injections and so on, and how they fare or such compared to the other aspects out there, right. So again this is a screening matrix, obviously, as the title indicates. So you can use that to screen out or screen in, let us say, the techniques that you can consider, I guess. So moving on, let us say we are now going to obviously start looking at the relevant aspects with respect to contaminated or sites contaminated with groundwater contaminated with various contaminants, right. And then once we are done with this particular set of aspects, we are going to look at soil and sediments which are contaminated, and how do I remediate those particular contaminated or sites which have what do we say now, soil and sediments contaminated, I guess, right. So two different cases or classifications that we are going to try to look at. One is when we have groundwater contamination, how do I remediate the site, and the other one is when I have soil or sediment contamination, how do I remediate the site. So in that context, obviously we are going to look at groundwater contamination, let us say. So in that context, groundwater contamination, let us say, we are going to primarily look at plume containment initially, right. So again, there are different examples wherein you can have what we say contaminated groundwater, let's say, right? And in that context, I think we also looked at one example at the start of this particular course, as in we looked at a particular case in Ghaziabad, where I believe we looked at a case where the groundwater was contaminated with chromium, and there was considerable outcry out there after considerable time anyway, and health effects, adverse health effects were observed by the relevant population. And only then did I think the political and the bureaucratic machinery, try to set the what do we say train in motion such that they looked at remediation of that particular contaminated site. Again, we looked at groundwater contamination in that particular scenario, and I think there the case was that you had some industries that looked at what we say involved heavy metals in their particular manufacturing process, and they did not dispose them in a proper manner or hold them in a not proper scientific manner, and thus you had contamination of this particular groundwater with the landfill. I believe whenever you had rainfall and you had what do we say permeation of this particular contaminated what do we say rainfall with the particular, not rainfall I guess, rainfall after contact with the contaminated soil reached the groundwater, and then you had contamination of the groundwater, right? So for example, I believe they had just the chromium piles out here on the surface, let's say land surface, and here you have the groundwater, let's say, and you had rainfall, let's say, and then through the subsurface and then contact with this particular groundwater, right? So you have contaminated groundwater here, and you had the affected population out here, let's say, and they were obviously had boring wells to have the water out, and they were ingesting the contaminated groundwater and so on, and the relevant issues there, I guess, right? So again, moving on, we did look at one particular case where they were actually pumping the water out, treating the water, and then disposing it in different ways. But here, before we look at pump and treat, we are going to look at containing the plume, as in I have a contaminated what do we say plume, as in here if I am looking at the plan view. So here is the source of my contamination and groundwater flow in this direction, and let us say if this is my contaminated plume, let us say groundwater contaminated plume. So rather than treating it or pump and treat is one option, I am just going to try to contain it, let us say, so that it does not spread to larger area, and thus leading to what do we say contamination to a wider extent, I guess. So I am trying to limit the extent of damage. You can consider this particular case as trying to limit the extent of damage. So how do I go about that, or look at plume containment, I guess, right? So if I go through to the next slide, here I have an example of what they were up to. It's a case of pump and treat, but in the first context we are going to look at plume containment before we move on to pump and treat. Again, this is pump and treat. They were pumping the groundwater out, treating it or using a reducing agent, I think sulfite, to reduce the chromium from oxidation state 6 to 3. At chromium at oxidation 3 precipitates out, let's say, and thus they are able to remove this particular chromium from that particular groundwater. You see, this is all the groundwater that they pumped out, and this is the treatment train in this particular direction, let's say. Yes, and I think here they were increasing the pH, I believe, maybe, and then adding the reducing agent, and here coagulation and flocculation out here, and so on. So we are going to look at the relevant videos in the next lecture, but for now I am just trying to give a picture of what or what are some of the aspects involved. So once they removed that chromium, again they were disposing it on land, I believe, because they could not treat it to the extent that they could re-inject the water into the groundwater, right, or into the subsurface. But here we are now looking at only plume containment for now, right. So again, what are some of these objectives for plume containment? Obviously I am trying to isolate the contaminant plume from the normal groundwater, let's say if I observe this particular contamination relatively early, let's say, what am I going to do? I am going to try to isolate the contaminated plume from the particular groundwater, let's say, and also prevent the plume from reaching an aquifer, as in, let's say, if there is a stream nearby, let's say, right. In general, how is it going to be the case? So if I have a stream here and it's flowing in this direction, and if I have a contaminated site here, this is the plan view again, plan view or top view, let's say. Typically groundwater flow direction would be towards that particular aquifer, let's say, or the stream, surface water body. I am just trying to look at, try to understand how you have your particular, what do we say, digital elevation model out there, let's say. So here I am trying to, what would happen if I let this contaminated groundwater reach this particular or recharge this surface water body? Then I would have, you know, the contaminant traveling over a wider extent of area, let's say, or distances, pardon me, and then contamination over a wider extent, let's say, right. So in that context, obviously I want to prevent this particular plume from reaching another aquifer, let's say, or water supply well or surface water body. In this context we look at a stream, I guess, right. So there are different objectives in mind when you are looking at plume containment. So in that context, let's look at what we have here. So how do I contain a plume? You know, there are different aspects, as in I can put in barriers. That's something we are going to discuss later. As in I can have barriers around that particular, if feasible, around that particular contaminated area and so on, so that there is no transport of the contaminant from that particular site to the groundwater and so on. But for example, I have a particular contaminated plume and I do not want to let it, you know, migrate further. So what can I do? I can pump it out, let's say. And what's the issue here, let's say? So here, let's say this is a particular case we are going to look at, and this is an ideal case. Obviously this is the what do we say, groundwater level, let's say, right. And here is my pump, let's say, or well, let's say, and this is the drawdown obviously that I see here, and I am going to pump the groundwater out, and this is what you would observe here. This is from the side view obviously, right. And here I have the top view. So here I have the top view, and obviously if this, for this case, all the groundwater would obviously, you know, flow towards the particular well. So as in if this is my contaminated plume, I can just plug one in the center and start pumping water out. This is again the top view, let's say. I can start pumping water out, and over time, let's say, or after a certain period of time, depending on the rate of your pumping, let's say you are going to, you know, capture the entire plume. But if you take a couple of seconds to try to look at this particular scenario and try to understand what the issue is, I guess you will see that it does not obviously reflect what would be the case out there in on the field or in the nature, let's say, right. Why is that? Obviously because, you know, groundwater in this particular case, as we see here, let's say if I look at the hydraulic gradient, you know, it's not going to be obviously flat, let's say, right. You are always going to have a gradient now, right. Again, you have a terrain, natural terrain, right, of the subsurface or earth, let's say, and your groundwater flow obviously direction typically tries to follow that particular terrain, let's say, depending obviously upon that particular aquifer characteristics and so on, let's say, right. But thus what we are trying to understand is that there is a groundwater flow, which is not the case that we considered here, and there is going to be a hydraulic gradient, right. So that's what we have here. So obviously if this is the hydraulic gradient, let's say, and now my groundwater would flow in this particular direction, let's say. So now if I plug my pump in now, let's say, and this is obviously the side view, and this is the top view, right. So if I plug it in now, let's say I will plug my pump in now and start pumping it out. So unlike the previous case, let's say, where you have symmetrical, what do we say, drawdowns and such, that's not going to be the case here. And especially the relevant aspects will be captured when I look at this particular top view. So when compared to the other case where all the plume was going to travel towards that particular pump, you are going to have flow lines that are not going to be captured by this particular pump here, right. So there is only a particular zone of influence for that particular pump, let's say, and there are considerable flow lines that will not be captured by this particular pump, let's say, right. So what are the different aspects that I need to consider now? I need to consider first how many pumps do I put in, let's say, what are the locations of these pumps, let's say, and what is the spacing between these pumps, and finally what is the rate of pumping from these particular pumps, let's say. So these are the aspects that there is particular design for, and we are going to go forth and look at that. Again, before we go further there, we need to look at what are the factors affecting the movement of this particular contaminated groundwater now, right. Say what are they now? So obviously aquifer characteristics, let's say, let's say, and typically we are considered what we say, we are considering hydraulic conductivity, I guess, right. Say, right. We consider hydraulic conductivity, let's say, right. and we are concerned with the energy or the hydraulic gradient, let us say, or the energy gradient, let us say, right, and we are concerned with the slope, pardon me, not the slope, I mean slope is considered out here. Obviously, we are concerned with the speed, let us say, that is equal to Ki, speed of groundwater flow, let us say groundwater flow velocity, and we are also concerned with aquifer thickness, I guess, right. Aquifer thickness. So, typically these are the factors that would, what do we say, affect your movement of the particular contaminated plume. Again, what are they? Hydraulic conductivity, again ease with which, let us say, your particular water, let us say, or contaminated water can flow through a particular media, let us say, and then hydraulic or energy gradient or the slope of that gradient, let us say, or slope energy slope, I guess gradient is slope, and velocity, which is K times I, and then aquifer thickness, let us say. These are the aspects which we typically need to consider here. So, how do I go about using this information and try to come up with an estimate about, let us say, the placing of the wells, number of wells, and so on, let us say. For example, let us say you, after looking at or considering a different number of monitoring wells, have this particular what do we say, piece of information, as in that your contaminated plume is this and your particular groundwater flow direction is this. You have the relevant aquifer characteristics, hydraulic gradient, velocity, and aquifer thickness. But how do I know where to place the wells? Obviously not in the center. Let us say, why is that? Because then I might not end up capturing all this particular portion, I might only capture only this particular portion, I might not capture all this plume. So, the key is to understand, let us say, or try to come up with a way to be able to scientifically what do we say, determine the number of wells, location of wells, spacing between the wells, and the rate at which you are going to pump out the relevant water from these wells, right. So, in that case, obviously you can look at groundwater or develop groundwater models, mathematical models, but typically that is time consuming and such, let us say, and is resource intensive. So, there are other what do we say, time tested methods pardon me, that people look at. So, one approach is obviously the guidelines based on simulation from Havendel et al. And published in, I think, groundwater volume, page number and year, let us say, right. So, let us just try to look at what they have here, and let me see where that is, that is out here, Havendel et al. So, what did they look at? Capture zone type curves, a tool for aquifer cleanup. So, they looked at simulations for this, let us say, and this is what I guess this is one of the particular cases. So, here we have a set of type curves showing the capture zones for a single pumping well located at the origin for various values of Q by BU, let us say. Q is the flow rate, B is the aquifer thickness, U is that velocity of groundwater flow, and let us say this is the groundwater flow direction. And so, they say that they can come up with a way to estimate these particular capture zone or this particular capture zone. So, let us see what they have here, let us see, right, and obviously they have this particular stagnation point, right. If this is my pumping well or location of my pump, let us say, or the well, I am going to have a stagnation point out here, yes, I am going to have a stagnation point. So, this particular boundary is my particular or determines the extent to which the contaminated plume can be captured by the well placed at this particular location. So, how do I go about getting that things done, or getting my particular aspects, again different aspects. So, here we look at a different case when I have two wells, I guess, and the spacing needs to be Q by 2 BU, right, say not spacing, I guess, from the width of the capture zone, let us say, from the center line Q by BU, and from the, and where does it need to be located? It needs to be, or the center line between these two wells needs to be located at distance of Q by 2 pi BU, let us say. Let me try to put that up in here, I guess, right. So, here they looked at different cases, one for one pumping well, they came up with that particular zone of influence, let us say, right, and they calculated the relevant distances. This is one particular distance that they calculated, and also this capture zone width, and also capture zone width far downstream, I guess, right. So, these are some of the aspects that they came up with or simulated, I guess, and then they also looked at simulation for what do we say, two wells, and if this is the center line here, and then again they were able to calculate the spacing required between the two wells, the capture zone width at the center of the wells, spacing from the center line to the stagnation point, because that is how you know where to locate the wells, and again capture zone width far upstream of the or far downstream of the particular contaminated plume, I guess, right. So, again moving back here, so again 3 wells, they considered 3 wells, again similar cases. So, based on that they came up with the general case, and here we have the relevant information. And what do we have here? We have the number of pumping wells 1, 2, 3 and n number, let us say, optimum distance between each pair of pumping wells, distance between the pumping wells, distance between dividing streamlines at the line of the wells, let us say, or the center line, distance between streamlines far upstream from the wells, let us see. So, let us try to understand this in our context, let us see. So, here we have the case for 2 wells. So, what do we have here? We have the distance at the center line, let us say, of the wells from the center, let us say, and this is Q by 2 BU. So, obviously this particular distance will be Q by BU, and we also have spacing for these 2 wells, that is also given, and also we have the spacing from the center line to this particular stagnation point, that is Q by 2 pi BU, and also we have this particular width, we have this particular width and the capture zone of this particular width. This is called obviously capture zone far downstream or upstream, let us say, depending on which context you are looking at. So, capture zone far upstream, I guess, let us say. So, obviously these are the 4 major aspects. Let us look at the table. So, the spacing between the wells for 1 well, 2 wells, 3 wells, 4 wells and n number of wells, Q by pi BU and so on, let us say 1.26, 1.2 Q by and 1.1 n Q by BU, I guess, let us say, right, or 1.1, pardon me. And here capture zone width at the wells 1.5 Q by BU, and let us try to understand that, and Q by BU for 2 wells. As we looked at that here, the capture zone width at the wells is this particular distance, capture zone width at this particular center line, I guess, and then capture zone width far upstream, and that is this particular case. And what is it for 2 wells? It is 2 Q by BU, I guess. So, again this is based on 2 Q by BU, and here this distance is Q by BU, let us say. So, how will this help me? So, I can understand, let us say, not try to understand, pardon me, try to analyze a particular contaminated plume and then try to look at the number of wells that are going to be looked at, what we say required to be able to capture that plume line. And again for this though, I need to be able to look at the threshold drawdown that I am going to look at, as in how do I decide, let us say, if I should place just 1 well at a high rate of pumping or 2 wells with relatively lower rates of pumping and so on and so forth. How am I going to be able to determine that particular aspect? Let us say it is going to be determined based on the acceptable level of drawdown, as in there is a maximum drawdown that is you can live with, as in your starting pumping here, let us say, you have a particular drawdown here obviously, right, and if I increase the rate of pumping, obviously my drawdown is going to be higher, let us say. I mean, I guess I am relatively poor at my drawing. So, obviously at a particular pumping rate this is my drawdown, and at a higher pumping rate this is my drawdown, right. So, obviously there are thresholds to this particular drawdown, as in if it is a confined aquifer, or let us say depending upon groundwater regulations in that area, let us say you do not want to affect the groundwater movement such that the other people will be affected. So, you are going to have to consider those aspects and take that into account, let us say. So, to get that into account, I need to be able to estimate the what we say drawdown, and for that I have a particular again what we say set of calculations. So, let us look at that. So, I have drawdown here that is going to be calculated based on a particular flow rate, right. So, what am I going to do? I am going to assume, or what is the approach here, let us say. I am going to assume, let us say, a particular case, as in I am going to start with 1 well and I am going to assume particular flow rate, and then go ahead and calculate the relevant drawdown and see if that is acceptable or not, let us say, right. So, here I have Q, let us say, and then I can calculate drawdown accordingly. What are some of the other aspects I need to have though? I have R, distance from center line of the well to the location at which I am considering, as in if this is my particular well and this is my drawdown, let us say, groundwater flow is in this direction obviously. So R would give me an idea about what is the distance from this center line of the well to the point at which I am considering this particular drawdown, I guess, right? Distance from center line of the well, and storage coefficient again act for property, transmissivity, product of hydraulic conductivity and saturated thickness, right? And drawdown, which is what I am trying to calculate, and time since pumping began. And this is the well function. I think people in hydraulics should be should hopefully try to recognize that. And well function, obviously, again, what do we have here? Approximations for well function. If u is between 0 and 1, we have a particular way to calculate well function. If u is greater than 1, we have another particular way to calculate well function, and then we can more or less obviously calculate the drawdown, I guess. So if this drawdown is within the acceptable limit, what would we do? We should say that the particular scenario is what do we say, meeting the relevant what do we say, thresholds with respect to drawdown, the plume capture boundary, and so on. But if it exceeds or does not meet one of these criteria, obviously I need to increase the number of wells, and then what do we say, again look at the relevant flow rates and so on, and then go ahead and calculate the relevant aspects, I guess. So I guess I am running out of time, so I will wrap it up for today, and then we are going to look at the relevant aspects in greater detail and maybe an example in the next session, I guess, right? And thank you for today.